For a century, cosmology grew from a speculative art into a precision science, and its crowning achievement is a single model of startling economy and power, the Lambda Cold Dark Matter model, the concordance cosmology of our age. It describes a universe that is spatially flat and expanding, governed by Einstein's general relativity, and filled with a strange mixture whose proportions we can now weigh. Roughly 68% of everything is dark energy, about 27% is cold dark matter, and a mere 5% is the ordinary matter of stars, planets, and people, with light and neutrinos making up a trace. What is astonishing is that this whole vast edifice, calibrated against the microwave background, the forging of the light elements, the clustering of galaxies, and the light of distant supernovae, is controlled by just 6 numbers. With those 6 parameters, the model fits a staggering range of data across 13 billion years of cosmic history. Yet the very precision that makes it a triumph has begun to expose its limits, and this chapter tells both stories, the model's grandeur and the cracks now appearing in it. The whole structure rests on a single simplifying assumption, the cosmological principle, that on the largest scales above a few hundred million light-years, the universe is homogeneous and isotropic, the same everywhere and in every direction. This is no idle guess, it is written in the near-perfect smoothness of the microwave background and in the 3-dimensional maps of the galaxies, and it singles out a unique family of geometries for spacetime, the expanding universe geometry first written down by Friedmann-Lemaitre-Robertson-Walker. In it, of cosmic expansion is captured by a single quantity, the scale factor, which measures how distances stretch with time. As space swells, the wavelength of traveling light is stretched along with it, and this is the origin of the cosmological redshift. The further back in time a photon set out, the more the universe has grown since, and the redder the light arrives. To read a galaxy's redshift is thus to read directly how much smaller the universe was when its light began its long journey to us. Feed this geometry into Einstein's equations, and out come the 2 Friedmann equations that govern the whole dance of expansion, relating the rate of expansion to the density of everything within and to the pressure that everything exerts. From them follows a natural measure, the critical density, the exact density that would render space perfectly flat, against which every component is weighed as a fraction. The tally of those fractions must sum to 1, and because each ingredient thins differently as the universe grows, radiation fastest, then matter, while dark energy does not thin at all, the equation for the expansion rate encodes the entire history of the cosmos, from a radiation-dominated dawn, through the long reign of matter to the present age of accelerating dark energy. A simple reckoning fixes the scale. At the measured expansion rate, the characteristic timescale of the expansion is about 14 billion years, and a full calculation gives the age of the universe as 13.8 billion years. The critical density itself is staggeringly low, about 5 hydrogen atoms in every cubic meter, yet it governs the fate of the whole cosmos. The first and richest of the model's observational pillars is the cosmic microwave background, the relic radiation set free when the universe, cooling through a redshift of about 1100, became transparent as its protons and electrons combined into neutral atoms. It shines today as a near-perfect blackbody, just under 3 degrees above absolute zero, and across it lie faint temperature ripples, 1 part in 100,000, first glimpsed by the COBE satellite, and later mapped in exquisite detail by WMAP and by Planck. Those ripples carry a series of acoustic peaks, the frozen music of sound waves that oscillated in the hot plasma before the light broke free, and each peak tells us something distinct. The position of the first reveals the geometry, showing space to be flat to within a percent. The relative heights of the peaks weigh the ordinary matter and the dark matter separately. In that single, information-dense pattern lies most of the precision of the entire 6-parameter fit, a fossil of the infant universe, read like the rings of a tree. The second pillar reaches back even further to the first few minutes, when the universe was hot and dense enough to be a nuclear furnace. In that brief window, Big Bang nucleosynthesis forged the lightest elements, the deuterium, the helium, the trace of lithium, in proportions that depend essentially on a single number, the density of ordinary matter. Deuterium is the finest gauge of all, for it is fragile, only destroyed in stars and never made anew, so its primordial abundance, measured in pristine gas clouds backlit by distant quasars, is a clean weighing of the cosmic baryons. And here lies one of the great triumphs of the hot Big Bang. The density of ordinary matter read from the light elements of the first minutes agrees to within a few percent with the value read from the microwave background released hundreds of thousands of years later, two utterly different epochs and kinds of physics, telling the same story. One sour note lingers, the stubborn lithium problem, where prediction and observation still disagree threefold, a puzzle yet unsolved. The remaining pillars brought the discovery of dark energy and the ruler that measures it. In the closing years of the 20th century, two teams set out to chart the expansion with Type 1a supernova, of the thermonuclear detonations of white dwarfs, whose uniform brightness makes them standard candles across billions of light years, and found the distant ones fainter than any slowing universe could explain. The expansion was speeding up. It was the first direct sign of dark energy, and it won the Nobel Prize. Woven through the galaxy maps, meanwhile, lay the baryon acoustic oscillations, the same primordial sound waves seen in the microwave background, now frozen into a preferred separation of about 150 megaparsecs between galaxies. This standard ruler, measured across cosmic time by great surveys like the Dark Energy Spectroscopic Instrument, calibrates the expansion history to percent precision. When all these independent probes, spanning the whole life of the cosmos, are fitted to one model, they converge on the same handful of numbers. That convergence is the empirical heart of concordance cosmology. The economy of the model is its most remarkable feature. 6 free parameters, the density of ordinary matter, the density of dark matter, the precise angular scale of the sound horizon, a measure of when the first stars reionized the gas, and the amplitude and tilt of the primordial ripples, suffice to fit the whole microwave sky and much beyond it. Everything else is derived. The expansion rate, the dark energy density, the age of the universe all follow. The benchmark values from the Planck satellite's final release have entered the textbooks, an expansion rate near 67, a total matter density of about 31%, a primordial tilt of 0.965, and an age of 13.8 billion years, with space flat to exquisite precision. The measurements even bound the combined mass of the ghostly neutrinos more tightly than any laboratory on Earth. That a model with so few knobs should fit so much is not remotely guaranteed, and that it does is precisely why it earned the name concordance. Yet a subtlety hides beneath the precision, and it matters greatly for what follows. The microwave background does not pin down every parameter on its own. Certain combinations are degenerate, producing nearly identical patterns on the sky. The most consequential entangles the expansion rate with the matter density and the curvature of space, which means the famous early universe value of the expansion rate is not a direct reading at all but an inference, one that holds only if the universe is assumed to be flat lambda cold dark matter. It is only by combining the microwave background with the galaxy surveys and the supernova that these degeneracies are broken and the numbers sharpened. This is why the concordance values come from joint fits of many probes, and it is the deep reason that the disagreements now emerging cannot be waved away. When a headline number is an inference rather than a direct measurement, a genuine discrepancy may be telling us that the model itself is incomplete. Consider first the dark matter, which makes up some 84% of all the matter in the universe, yet neither emits nor absorbs light. The evidence for it is overwhelming and gathered across every scale. The rotation curves of spiral galaxies stay stubbornly flat far beyond the visible disk, where the stars thin out and the orbital speeds should fall, work pioneered by Vera Rubin and Kent Ford in the 1970s, betraying vast halos of unseen mass. Decades earlier, Fritz Zwicky had found the galaxies in clusters moving far too fast to be bound by their visible matter alone. Gravitational lensing weighs the mass of clusters directly and finds most of it dark. The third peak of the microwave background demands it, and the very growth of structure, from the smooth early universe to today's cosmic web, is impossible in the time available without it. On scale after independent scale, the same silent verdict: there is far more here than meets the eye. The word cold is the crucial qualifier. Cold dark matter means particles that were moving slowly when structure began to form, so that they could clump on small scales and seed a bottom-up assembly, small clumps merging into ever larger ones, exactly the hierarchical growth that simulations reproduce and the galaxy surveys confirm. Hot, fast-moving dark matter would have smeared out the small structures and is ruled out as the main component. But what is the particle? Here lies one of the deepest open questions in all of science. The leading candidates have long been the weakly interacting massive particles, whose predicted abundance falls naturally close to the observed value, a coincidence so tidy it was called the miracle, and the action, a feather-light particle, born to solve a separate puzzle in the physics of the strong force, which would serve equally well as the cold dark matter. Sterile neutrinos, primordial black holes, and ultralight fields all remain in contention. The substance is certain, its identity is not. For decades, physicists have hunted the dark matter particle directly, building exquisitely shielded detectors deep underground to catch the faint recoil of a nucleus struck by one passing through. They have found nothing. The largest of these xenon detectors, the LUX Zeppelin experiment, and its rivals, have set ever tighter limits with no signal above the background, squeezing the once favoured massive particle into an ever smaller corner and turning attention toward the action and lighter, more elusive candidates. Dedicated action experiments now scan its plausible range. Meanwhile, a set of small-scale puzzles, galaxies with fewer satellites than the simulations predicted, or gentler central densities, was once read as a failure of cold dark matter, but the consensus now is that these are mostly matters of messy ordinary astrophysics of supernova winds and star formation in the smallest halos, rather than cracks in the cosmology. The distinction is worth holding on to. That dark matter exists as a gravitating substance is beyond serious doubt. What it is made of is genuinely unknown. The largest term of all in the cosmic budget is the strangest. Dark energy, the smoothly spread component whose negative pressure drives the acceleration of the expansion. Its character is captured by a single number, its equation of state, the ratio of its pressure to its energy density. A cosmological constant, mathematically identical to the energy of empty space itself, has an equation of state of exactly -1, and any component more negative than -1/3 will drive the cosmos apart. The measurement sits squarely on -1, fully consistent with a simple constant. But that constant carries two profound puzzles. Its predicted value from summing the restless energy of the quantum vacuum exceeds the observed value by up to 120 orders of magnitude, perhaps the worst prediction in the history of physics. And why should dark energy and matter, which evolve so differently, be comparable in strength just now in our own brief epoch? Neither puzzle has an accepted answer. These puzzles have long motivated a bolder idea that dark energy is not a constant at all, but a slowly evolving field whose strength changes over cosmic time. For years, the data gave no reason to prefer it, but that may be changing. In the middle years of this decade, the dark energy spectroscopic instrument, mapping the acoustic ruler across millions of galaxies and combining it with the microwave background and the supernova, reported a mild but persistent preference for evolving dark energy over a pure constant, at a significance of somewhere between 3 and 4 standard deviations, depending on which supernova sample is used. The best fit hints that dark energy was stronger in the past and is now weakening, a pattern like the gentle thawing of a scalar field. This is not yet a discovery. It falls short of the 5 standard deviation threshold physicists demand, and it may yet dissolve into systematic error. But it is the most serious empirical challenge to the cosmological constant in 2 decades, and the coming flood of data from DESI, from Euclid, and from the Rubin Observatory should settle whether it stands. The standard model is silent about where its primordial ripples came from. That role falls to cosmic inflation, a hypothesized burst of near-exponential expansion in the universe's very first fraction of a second. Proposed around 1980 by Alan Guth, Andre Linde, and others, it was designed to cure 3 deep ailments of the older picture. Why is the microwave background so uniform across regions that could never have been in causal contact? The horizon problem. Why is space so precisely flat when ordinary expansion drives it away from flatness? The flatness problem. And where are the heavy magnetic monopoles that grand unified theories predict? A brief episode of exponential stretching solves all 3 at a stroke, blowing a tiny causally connected flat patch up to encompass everything we can see and diluting the monopoles to nothing. But inflation's greatest legacy is quantitative. The quantum jitter of the field driving it, stretched to cosmic scales, becomes the seed of all structure, and it predicts a spectrum of ripples very nearly, but not exactly, the same on all scales. That faint predicted tilt, measured at 0.965, is one of inflation's clearest triumphs. The cleanest remaining test of inflation is a hunt for a whisper from the first instant, primordial gravitational waves. Inflation should have set spacetime itself ringing, and those ripples would leave a faint, distinctive swirl in the polarization of the microwave background. a pattern no other process can easily mimic. Despite intense searching, none has been found, and the upper limit on their strength grows tighter with every experiment, already excluding several once popular versions of inflation while leaving many others alive. And so inflation must be described honestly. It is a spectacularly successful framework, accounting for the flatness, the uniformity, and the very spectrum of the seeds of structure, but it is not a single settled theory. Its energy scale is unknown, the identity of the field that drove it is unknown, and deep conceptual debates over eternal inflation, over what it even means to make predictions in a universe that inflates forever, remain unresolved. It is the leading paradigm for the birth of structure, not yet an established mechanism, on the firm footing of nucleosynthesis. Now to the sharpest crack in the whole edifice, the Hubble tension. The expansion rate of the universe can be found in two utterly different ways, and they no longer agree. The early universe route reads it from the microwave background and the acoustic ruler, anchored to physics calculable from first principles, and yields a value near 67. The late universe route climbs the cosmic distance ladder, using geometry to fix the distances to nearby Cepheids variable stars, using those Cepheids to calibrate the true brightness of type 1a supernova, and using those supernova to measure the expansion far out in the smooth cosmic flow. Executed meticulously by the distance ladder team, it yields a value near 73. The gap between them is some 5 or 6 units, a discrepancy now at roughly the 5 standard deviation level, far beyond any plausible statistical fluke. And the James Webb Space Telescope, scrutinizing the Cepheids afresh, has so far only strengthened the local measurement rather than dissolving it. The heart of the matter is that these two methods measure the very same quantity through entirely different physics and different epochs. So if neither harbors a hidden error, then the model that bridges them, converting the early universe into a predicted expansion rate, must be missing something. Enormous effort has hunted for that hidden error on both sides, and none has yet been found. Proposed cures cluster into two camps. Some inject a little extra energy into the universe just before the light broke free, an early, dark energy that shrinks the acoustic ruler and lifts the inferred expansion rate, but it tends to worsen other fits and demands delicate timing. Others alter dark energy in the recent universe, but struggle to move the number without spoiling the beautiful agreement of the supernova and the acoustic ruler. No single modification cleanly mends the tension while preserving every other success of the model, which is exactly why it is taken so seriously. Whether it heralds new physics or a subtle unfound systematic remains, for now, genuinely undecided. A second, milder discord concerns not how fast the universe expands, but how clumpy it has become. A measure combining the amplitude of matter fluctuations with the matter density can be predicted by evolving the microwave background forward, and the great surveys of gravitational lensing, which map the clumping of mass in the recent universe, have tended to find it slightly smoother than predicted, at the level of 2 or 3 standard deviations. For a time this looked like another possible sign of new physics, but the picture has softened. The latest lensing analyses with better calibration have edged back toward agreement, and much of the residual gap now seems to stem from the messy feedback of galaxies and from measurement systematics rather than from cosmology. A newer surprise came from the James Webb Telescope, which spied galaxies at cosmic dawn so massive and bright they seemed too big, too soon for the standard model, but here too, refined measurements and a fuller accounting of early star formation have largely brought the counts back within expectation. Both episodes counsel caution in reading every anomaly as a revolution. The standard model has rivals, and testing it against them sharpens what it must explain. The boldest challenge to dark matter is modified Newtonian dynamics, proposed by Mordechai Milgrom in 1983, which posits that gravity itself departs from Newton's law below a certain tiny acceleration, reproducing the flat rotation curves of galaxies with no dark matter at all. On the scale of single galaxies it is genuinely successful, but it falters on larger scales. Clusters still demand unseen mass even within it, and it cannot reproduce the full pattern of the microwave peaks. Its most famous stumbling block is the bullet cluster, a colossal collision of two clusters in which the gravitational mass mapped by lensing is seen cleanly separated from the hot gas that carries most of the visible matter, precisely what one expects if collisionless dark matter sailed through, while the gas was shocked and left behind, and a great swat of modified gravity theories was swept away when a neutron-star merger in 2017 showed gravitational waves, and light arriving together after a 130-million-year journey, fixing the speed of gravity to that of light with staggering precision. The coming decade is designed to answer these very questions, and a suite of magnificent instruments is now turning to the task. To map dark energy's evolution and test the tantalizing hint that it changes with time, the Rubin Observatory, the Euclid mission, and the Roman Space Telescope will chart the expansion and the growth of structure with unprecedented reach. To pin down the expansion rate free of the fickle distance ladder, gravitational wave standard sirens will read distance straight from the ringing of merging black holes, while ever-sharper microwave measurements tighten the early universe anchor. To probe the first instant, next-generation experiments will chase the primordial gravitational waves toward sensitivities that would measure the energy scale of inflation itself, and to unmask the dark matter particle, new detectors will press down toward the irreducible haze of cosmic neutrinos that marks the ultimate limit of the search, while action hunters scan fresh ground. A laboratory detection would transform dark matter, at a stroke, from an astronomical inference into a known piece of nature. Two great questions hang over it all. First, whether the anomalies now flickering at the edges of the data, the Hubble tension, the clumpiness discord, the hint of evolving dark energy, the early galaxies are so many unrelated flukes and systematics, or facets of a single, missing piece of physics waiting to be found. Second, whether the deepest puzzles of all, why the cosmological constant is so absurdly small, why we live at the one moment when matter and dark energy are comparable, and how gravity is ever to be married to the quantum can be brought within reach of observation, or must remain, for now, in the realm of speculation. And so the Standard Model stands in a curious double light. It is among the most precisely tested theories in all of science, accurate to the percent level across 13 billion years of cosmic time, and yet its three great pillars, inflation, dark matter, and dark energy, are each at the level of fundamental physics a profound mystery. We have measured the universe to extraordinary precision. We have not yet understood what most of it is.